somewhere above your head right now. The temperature of empty space sits at nearly 273 degrees Celsius below zero. That number sounds abstract until you realize it means something almost nothing has ever meant on Earth. It means the absence of almost all motion. This is why astronauts who lose contact with a spacecraft do not freeze in seconds the way people assume. Why the coldest known place in the entire universe is not empty space at all, but a cloud of gas drifting near a star nearing the end of its life. And why the leftover glow of the Big Bang itself is technically warmer than some places we can measure today. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. Cold, as most people understand it, is a feeling. It is wind against skin, or the ache in your fingers after too long outside without gloves. But that feeling is not what cold actually is. Cold is the absence of a very specific kind of motion. Every particle of matter in the universe, every atom, every molecule, is constantly jittering, vibrating, colliding with its neighbors. Temperature is simply a measurement of how much that jittering is happening. A hot object has particles slamming into each other with tremendous energy. A cold object has particles moving sluggishly, barely disturbing one another. When physicists talk about temperature, they use a scale that starts not at the freezing point of water, but at the point where all of that motion theoretically stops completely. That point is called absolute zero. On the Kelvin scale, which scientists prefer for exactly this reason, absolute zero sits at 0 Kelvin. In more familiar terms, that is about 273 degrees below 0 Celsius. At that temperature, in principle, particles would stop vibrating entirely. No motion, no jitter, no thermal energy left to give away. It is the coldest anything could ever theoretically be. And here is the strange part, one of the deepest truths in physics. Nothing in the universe has ever actually reached it. Not once, not anywhere, not through any process nature has stumbled upon in more than 13 billion years of cosmic history. Quantum mechanics forbids it. Even in the most isolated, most shielded, most carefully engineered laboratory conditions on Earth, where scientists have cooled matter to fractions of a billionth of a degree above absolute zero, there remains a tiny, irreducible amount of motion. It is called zero-point energy, and it is baked into the fabric of reality itself. Particles can get astonishingly close to absolute stillness. So when someone says space is cold, what they actually mean is that space is close to this theoretical floor, but not sitting at it. And understanding how close and why, and what shapes that coldness across different regions of the universe, requires abandoning almost everything intuition tells you about temperature. Because space does not behave the way a room behaves, or the way an ocean behaves, or the way anything on the surface of a planet behaves. Space is not full of cold air waiting to steal your body heat. Space, for the most part, is not full of anything at all. And that absence changes everything about what cold even means once you leave Earth's atmosphere behind. To understand why, you have to separate two ideas that feel identical on Earth, but are completely different in a vacuum. The first idea is temperature. The second idea is heat transfer. On Earth, these two things are tangled together so thoroughly that we never bother separating them. Step outside on a freezing morning without a coat, and the air around you, filled with billions of molecules per cubic centimeter, is constantly colliding with your skin. Each collision carries away a tiny bit of your body's thermal energy. Multiply that by the sheer density of the atmosphere, and heat drains from you rapidly through a process called conduction, molecule bumping into molecule, passing energy along like a relay race. Wind makes this worse. through convection, constantly replacing the thin layer of slightly warmed air right against your skin with new, cold air that has not yet absorbed any of your warmth. This is why wind chill feels so much more dangerous than still cold air at the same temperature. It is not that the air itself is colder. It is that the air is stealing your heat faster. Now take away the air entirely. Take away every single molecule. That is what much of space actually is, particularly the vast stretches between stars and galaxies. Interstellar space, the region between star systems, contains roughly 1 atom per several cubic centimeters in the densest clouds, and far less than that in the emptiest voids. Compare that to the air around you right now, which contains something on the order of 25 quintillion molecules in that same volume. The difference is not small. It is not even in the same universe of scale. Space, in most places, is emptier than the most perfect vacuum humans have ever manufactured inside a laboratory. And without molecules bumping into your skin, conduction simply cannot happen. There is no wind to blow because wind requires air molecules, and there are none to move. Convection cannot happen either, for the same reason. This leaves exactly one way for heat to escape, a body floating in the vacuum of space, and it is a slower, quieter process than most people imagine. That process is called radiation. Every object with a temperature above absolute zero emits electromagnetic radiation, invisible infrared light carrying energy away from its surface. This happens constantly, everywhere, all the time, on Earth too, though it is usually overwhelmed by the much faster losses from conduction and convection. In the vacuum of space, radiation becomes the only mechanism left, and radiation is a far less efficient thief of warmth than direct contact with cold matter. This single fact overturns one of the most common misconceptions people carry about space. The assumption that an astronaut exposed to the vacuum would instantly flash freeze, skin turning to ice within moments, is simply wrong. In reality, unprotected exposure to the vacuum of space is dangerous for entirely different reasons, and temperature is almost never the first thing that would hurt a person. The far more immediate threats are the loss of breathable pressure, which can cause the moisture on the tongue and eyes to boil away within seconds due to the drop in pressure, and the rapid loss of consciousness from oxygen deprivation, typically within about 15 seconds. A person would lose consciousness long before body heat became a significant concern, and actual freezing, if it happened at all, would take a much longer time than fiction suggests. Precisely because radiation alone is such an inefficient way to lose warmth compared to conduction. In fact, in direct sunlight, an exposed body would gain heat rather than lose it, because unfiltered solar radiation without an atmosphere to absorb and scatter, it is considerably more intense than sunlight filtered through a planet's air. This single detail illustrates something crucial about cold in space. It is not a uniform blanket sitting over everything equally. It is wildly, almost violently uneven, shaped entirely by whether or not something happens to be facing a source of radiation. Consider the surface of the moon, a body with essentially no atmosphere to average out temperatures the way Earth's air does. During the lunar day, when the surface faces the sun directly, temperatures at the equator can climb to around 127 degrees Celsius, hot enough to boil water if there were any liquid water sitting exposed on the surface. Then, as the same patch of ground rotates into the 2-week-long lunar night with no atmosphere to hold any residual warmth in place, temperatures plunge to around -173 degrees Celsius. That is a swing of exactly 300 degrees Celsius between day and night on the same rock, with nothing but the presence or absence of direct sunlight causing the difference. There is no wind to average things out. There is no ocean to store heat and release it slowly. There is only bare rock, radiating whatever warmth it has absorbed straight out into space the instant sunlight stops arriving. Permanently shadowed craters near the lunar poles, places sunlight has arguably never reached in billions of years because of the moon's nearly upright rotational axis, holds some of the coldest measured temperatures anywhere in the solar system, dropping below -240 degrees Celsius, a mere handful of degrees above absolute zero itself. These craters are colder than the surface of Pluto. They are colder than the average temperature of interstellar space itself, and they exist not because they are far from the sun, but because they are permanently turned away from it, trapped in shadow by the geometry of crater walls that never let a single photon of sunlight inside. This tells you something profound about how cold actually works away from a planet's protective atmosphere. Distance from a heat source matters, certainly, but orientation matters just as much, sometimes more. Mercury, the planet closest to the Sun, demonstrates this same principle on an even more extreme scale. Mercury has essentially no atmosphere worth mentioning, nothing thick enough to trap heat or distribute it evenly. During the day, with the Sun blazing at a distance of only about 58 million kilometers, surface temperatures on the sunlit side can reach around 430 degrees Celsius, hot enough to melt lead. Yet craters near Mercury's poles, permanently shadowed in the same way as the Moon's polar craters, harbor water ice, frozen and stable. At temperatures below -170 degrees Celsius, on the very same planet that boils, lead a short distance away. A planet closer to the Sun than any other in our system still manages to hide ice in permanent shadow, because temperature in space is not a single number describing a whole world. It is a description of exposure, of geometry, of whether or not a particular patch of surface happens to be looking toward a source of radiation at any given moment. This becomes even more dramatic once you leave planetary surfaces behind entirely and consider objects orbiting freely in the vacuum, with nothing but their own structure separating sunlit sides from shadowed sides. The International Space Station, orbiting Earth roughly every 90 minutes, passes in and out of Earth's shadow constantly, experiencing something like 16 sunrises and 16 sunsets every single day. The sun-facing side of the station's exterior can reach temperatures over 120 degrees Celsius. The shadowed side, at the very same moment, can plunge to around -157 degrees Celsius. That temperature difference exists simultaneously on the same structure, separated by nothing more than which direction a particular panel happens to be facing. Engineers who design spacecraft spend enormous effort solving exactly this problem, because a vehicle that gets scorched on one side and frozen on the other, over and over, every 90 minutes, for years, needs materials and coatings that can survive that kind of relentless thermal cycling without cracking, warping, or failing. This is why spacecraft are often wrapped in multiple layers of reflective insulation, thin gold or silver-colored blankets that look almost decorative but are actually doing critical work, bouncing away excess solar radiation on the hot side while trapping what little heat remains on the cold side. It is also why spacecraft slowly rotate in a maneuver engineers sometimes call the barbecue roll, turning steadily like a rotisserie, so that no single side bakes in sunlight or freezes in shadow for too long, spreading the thermal stress evenly across the entire vehicle. Without this constant, careful management of exposure and shadow, no human-made object could survive long in the vacuum. Not because space itself is uniformly hostile, but because it swings between extremes with a violence that no material handles well if left facing one direction for too long. moving beyond our own solar system into the vast emptiness between star systems. The character of cold changes again, and here the story becomes genuinely strange. Interstellar space, far from any star's direct light, might seem like it should be the coldest environment imaginable, an endless void with nothing to warm it at all. And in one sense, this expectation is correct. The vast, nearly empty stretches of the interstellar medium can measure remarkably close to just a handful of degrees above absolute zero when you look at regions far from any star's influence. But this is where a genuine paradox emerges, one that puzzled scientists analyzing data sent back by the Voyager spacecraft after they crossed into interstellar space. When Voyager 1 crossed the boundary separating our sun's protective bubble, called the heliosphere, from true interstellar space, instruments detected something that seemed contradictory at first glance. The plasma in that region, the extremely thin soup of charged particles drifting between stars, registered temperatures in the tens of thousands of degrees when measured by the kinetic energy of individual particles. That number sounds like it should mean interstellar space is scorching hot, hotter than the surface of many stars. But this apparent contradiction reveals something crucial about what temperature actually measures at the level of physics, something that gets lost when we casually use the word cold to describe an entire region of space. Temperature, at its core, describes the average kinetic energy of particles, how fast they are moving and colliding. It does not, by itself, describe how much total thermal energy is present, and it does not describe how something would feel to a human body or any object placed inside that environment. The plasma in interstellar space is indeed made of individual particles moving at tremendous speeds, giving it a technically high temperature by the strict definition physicists use. But those particles are so sparse, so spread out, so infrequent in their collisions with anything, that despite their individual high speed, they carry almost no ability to transfer that energy to a larger object. Imagine a handful of extremely fast-moving marbles rattling around inside an enormous empty warehouse, each one occasionally striking a wall with tremendous force, but so rarely and so few in number that the warehouse itself never meaningfully warms up. That is roughly the situation in the thin plasma of interstellar space. The particles are fast, technically hot by the physics definition, but so few and far between that a spacecraft or an astronaut placed in that environment would still lose heat overwhelmingly through radiation into the surrounding cosmic emptiness. Not gain it from occasional collisions with scorching but sparse particles. This is why scientists sometimes distinguish between kinetic temperature, which describes particle speed, and the practical, experiential cold that any solid object would actually feel, which depends far more on radiative balance, how much energy an object absorbs from starlight and cosmic background radiation, versus how much it radiates away into the surrounding dark. For almost any solid object, floating far from a star, radiative balance settles at a temperature only a few degrees above absolute zero, regardless of how energetic the sparse surrounding plasma particles happen to be. Space, in other words, can be simultaneously and truthfully described as blisteringly hot by one measurement and bitterly cold by another. And both descriptions are correct because they are measuring fundamentally different things. This is one of the reasons space is such a genuinely strange environment to reason about, using instincts built entirely on Earth's atmosphere, where density is high enough that these distinctions rarely matter, and temperature behaves the way we expect it to. Now consider a different kind of cold, one that has nothing to do with distance from stars, or shadow, or sparse plasma, but comes instead from the leftover afterglow of the universe's own birth. fill every direction of the sky with an almost perfectly uniform bath of microwave radiation, so faint and so evenly spread that it took decades after its theoretical prediction before instruments sensitive enough to detect it clearly were built. This is the cosmic microwave background, radiation released roughly 380,000 years after the Big Bang, when the early universe had cooled enough for light to travel freely for the first time, rather than being trapped and scattered by a dense fog of charged particles. That ancient light has been stretching ever since, as the universe itself has expanded, and stretching light lowers its energy, shifting it from what was originally something closer to visible or infrared light into the microwave portion of the spectrum we detect today. Measured very precisely, this cosmic background radiation corresponds to a temperature of about 2.725 Kelvin, just a few degrees above absolute zero. This number matters enormously, because it sets something like a cosmic floor, a minimum baseline temperature that fills literally every corner of observable space, whether near a galaxy or in the emptiest void between superclusters. Nowhere in the observable universe, no matter how far from any star, can naturally cool below this background bath of ancient radiation. Because that radiation is constantly arriving from every direction, depositing a tiny but non-zero amount of energy everywhere it touches, gently warming even the emptiest voids between galaxy clusters, just enough to keep them from ever slipping any further toward absolute stillness on their own. This raises an obvious and fascinating question. If the cosmic microwave background sets a universal floor, gently warming every corner of space to at least a few degrees above absolute zero, could anything in nature possibly be colder than that floor? The answer, remarkably, is yes, and the place where it happens is one of the strangest objects in the observable universe. Roughly 5,000 light-years from Earth sits an object known as the Boomerang Nebula, a cloud of gas and dust being expelled by an aging star in its final stages before becoming a white dwarf. As this star sheds its outer layers, it is doing so in an extraordinarily rapid, extraordinarily violent stellar wind, gas rushing outward from the star at speeds around 164 kilometers per second. This rapid expansion is the key to the nebula's astonishing coldness. Gas that expands quickly, cools rapidly, following the same basic physics that makes the gas rushing out of a compressed air canister feel cold against your skin, though on a scale almost impossible to fully picture. The expanding gas in the Boomerang Nebula is rushing outward so fast and expanding so dramatically that it has cooled to approximately 1 Kelvin, just 1 degree above absolute zero. That makes it, as far as astronomers have been able to measure anywhere in the observable universe, the single coldest known natural place, colder even than the leftover glow of the Big Bang itself, colder than the depths of interstellar space between galaxies, colder than any planet, moon, or shadowed crater humans have ever measured. An aging star, in the act of shedding its final layers, has created a pocket of space colder than the ambient temperature of the entire universe around it. A strange and almost poetic detail that the coldest known place in existence was not formed by distance from warmth, but by the violent, rapid expansion of gas flung outward from something that was, until recently, blazing with stellar fire. This single object forces a reconsideration of what people usually assume about cold in space. The assumption that distance from stars, or the vast emptiness of the void itself, is what produces the deepest cold. In reality, the most extreme cold discovered so far came from motion, from the physics of rapid expansion, not from simple isolation or emptiness. Contrast this with what happens at the opposite end of stellar evolution, in the compact, extraordinarily dense remnants left behind after certain kinds of stars finish burning entirely. Neutron stars. The collapsed remains of massive stars that ended their lives in supernova explosions are born blisteringly hot, with core temperatures immediately after formation reaching around 100 billion Kelvin. Temperatures with no everyday comparison possible, hotter than almost anything else known to exist. But neutron stars, much like the expanding gas of the Boomerang Nebula, cool over time, radiating their tremendous heat away into the surrounding emptiness across millions of years. A neutron star born 1 million years ago has already cooled dramatically compared to its initial formation, dropping to surface temperatures that, while still far hotter than anything on Earth, represent an enormous decline from its violent birth. Given enough time, on scales of many trillions of years, far longer than the current age of the universe itself, these stellar remnants theoretically continue cooling, asymptotically approaching, though never quite reaching, the same cosmic background floor that fills the rest of space. White dwarfs, the compact remnants left behind by stars roughly the mass of our own sun, follow a similar pattern, born intensely hot after their parent star sheds its outer layers, then cooling steadily over billions of years. Some of the oldest white dwarfs discovered in our galaxy, having already cooled enough that astronomers refer to them, somewhat informally, as black dwarfs in waiting, remnants so cool and so dim they become almost impossible to detect against the darkness surrounding them. No actual black dwarf is thought to exist yet anywhere in the universe, because the process of cooling from a white dwarf down to that theoretical endpoint takes far longer than the roughly 13.8 billion years the universe has existed so far. This detail hints at something enormous, something that stretches the concept of cold in space out to a genuinely cosmic scale, far beyond individual stars or nebulae. The universe itself, considered as a whole, single, evolving system, is getting colder, and has been getting colder continuously since the Big Bang, and will likely continue getting colder for an almost unimaginable stretch of time still to come. This happens because the universe is expanding, and has been expanding since its birth, stretching the space between galaxies, between clusters, between essentially everything, and that stretching applies not only to matter but to radiation, cooling the cosmic microwave background itself along the way, from what was once a blistering plasma hotter than the core of any star, down to the mere few degrees above absolute zero we measure today. This cooling has been remarkably steady across cosmic history, moving from an almost inconceivably hot, dense state in the earliest fractions of a second after the Big Bang, through a long series of cooling milestones, the formation of the first atoms, the emergence of the first stars, the slow assembly of galaxies, all the way down to the frigid background we observe now, nearly 14 billion years later. And this cooling trend, driven by the ongoing expansion of the universe, is not expected to stop or reverse. Current observations suggest the expansion of the universe is not merely continuing, but accelerating, driven by a mysterious phenomenon researchers call dark energy, something that appears to be pushing galaxies apart from one another at an ever-increasing rate. If this acceleration continues indefinitely, as most current evidence suggests it will, the long-term future of the cosmos points toward a scenario physicists sometimes call the heat death of the universe, or more formally, the state of maximum entropy. In this far future scenario, stretching across timescales that make even the current age of the universe look like a single passing moment, stars will exhaust their fuel one by one and stop forming entirely, because the raw material needed to build new stars will eventually become too spread out and too cold to collapse into new stellar furnaces. Galaxies will drift apart from one another, carried by the relentless expansion of space itself, eventually moving so far apart that light from one galaxy could never reach another, isolating every remaining structure in its own private, ever-darkening bubble. Black holes, the last significant sources of concentrated mass remaining in this far-future universe, will themselves very slowly radiate away their mass through an extraordinarily faint process theorized by physicist Stephen Hawking, called Hawking radiation, evaporating over timescales so long they defy ordinary comprehension. Some of the largest black holes, theoretically requiring on the order of 10 to the power of 100 years to fully evaporate, a number so large it dwarfs the current age of the universe by an almost unimaginable margin. After the black holes are gone, after the last flickers of radiation have faded, what remains is a universe approaching, though technically never quite reaching, a state of complete thermal equilibrium, an almost perfectly uniform, almost perfectly cold expanse, where temperature differences, the very thing that allows energy to flow and work to be done and processes to unfold, have essentially vanished. At that point, in this theoretical far future, entropy, the measure of disorder physicists use to describe how energy spreads out and becomes less useful over time, will have reached its maximum possible value, and nothing meaningful will be able to happen anymore. Not because matter or energy will have vanished, but because there will be no more temperature differences left to drive any further change. This is, in the most literal sense that physics can currently describe, the coldest the universe will ever become. An endpoint some researchers estimate lying unimaginably far in the future, so distant that comparing it to the current age of the universe is a bit like comparing the age of a single second to the entire history of human civilization. It is worth pausing here to notice something important about this entire story. From the shadowed craters of the moon to the far future heat death of the cosmos, cold, throughout all of it, has never been an active force, reaching out to grab something and freeze it, the way it can sometimes feel in casual language, as though cold were something with its own energy, its own presence, pushing itself onto whatever it touches. Cold, in every single case explored here, is simply the absence of something else, the absence of nearby radiation, the absence of dense matter to conduct heat away quickly, the absence of motion at the particle level, the absence of any remaining temperature difference capable of driving further change. This reframing matters, because it changes how strange and beautiful the coldness of space actually becomes once you understand the mechanism behind it. Space is not some vast, hostile ocean of cold, reaching out to freeze anything careless enough to drift into it. Space is mostly emptiness, and emptiness, without matter close by to conduct heat away or convect it in currents, is remarkably slow at stealing warmth from anything, compared to how quickly Earth's dense atmosphere and oceans do the same job. The true danger of space, for any living thing or any fragile piece of engineering, comes not from an aggressive coldness reaching out to attack, but from imbalance. From one side facing a blazing, unfiltered source of radiation, while the other side faces the profound emptiness of the void, with almost nothing in between to smooth out that difference the way an atmosphere does here on Earth. This is why the engineering solutions humans have developed to survive and operate in space focus so heavily on managing this imbalance, rather than fighting cold itself as though it were some monster to be defeated. Multi-layer insulation blankets, the shiny gold and silver material visible on almost every spacecraft and satellite, work not by generating warmth, but by controlling how much radiation passes through in either direction, reflecting away excess heat on sunlit sides while trapping whatever thermal energy remains on shadowed sides. Spacesuits worn by astronauts during spacewalks contain multiple layers for exactly this reason. some designed to reflect solar radiation away during the intensely hot, sunlit portions of an orbit, others designed to retain body heat during the intensely cold, shadowed portions, with small heaters supplementing warmth in specific areas like gloves and boots, where extremities are especially vulnerable to the slow but steady radiative heat loss that does eventually occur, even without conduction or convection to accelerate it. Even something as simple as the color and texture of a spacecraft's outer surface becomes a critical engineering decision, because different materials absorb and radiate energy at different rates, a property engineers describe using something called emissivity. How efficiently a surface radiates away thermal energy compared to how efficiently it absorbs incoming radiation. Getting this balance wrong on a satellite or a rover sent to another world can mean the difference between electronics surviving for years and equipment failing catastrophically within days. Cooked on one side, frozen solid on the other, with no atmosphere anywhere nearby to average things out the way it constantly does here at home. On the surface of Earth, without most of us ever realizing just how much protective, moderating work our atmosphere quietly performs every single day. That protective moderation is, in fact, one of the most underappreciated gifts our planet provides. Earth's atmosphere, combined with its oceans, acts as an enormous thermal buffer, absorbing incoming solar radiation during the day and releasing it slowly overnight, smoothing out what would otherwise be temperature swings, just as extreme as those found on the airless moon, a mere 384,000 kilometers away. Without this atmospheric buffering, Earth's day and night temperature swings would likely resemble the moon's punishing 300 degrees Celsius difference, rather than the comparatively gentle shifts most regions on our planet experience between day and night. This buffering effect is part of why life as we know it could take hold and persist here, why liquid water could remain stable on the surface for billions of years, why chemistry had the steady, moderate conditions needed to slowly assemble into biology, rather than being blasted by extreme heat every day and plunged into extreme cold every night, the way most other rocky surfaces in our solar system experience, without any atmosphere thick enough to moderate the difference. Every time you feel a gentle breeze or notice that nighttime is chilly but not instantly lethal, you are experiencing the quiet, constant work of an atmosphere doing exactly what the vacuum of space cannot do at all, redistributing thermal energy through conduction and convection, keeping temperature differences from becoming as violent and immediate as they are on the Moon, on Mercury, or on the exterior panels of any spacecraft orbiting without that same protective layer. There is a strange twist to this entire story, one that most people never consider. The coldest known temperature anywhere in the observable universe was not actually found in space at all. It was created here on Earth, inside a laboratory, by human hands. Physicists working with lasers and magnetic fields have developed techniques capable of slowing atoms down to speeds barely above a crawl, stripping away almost all of their thermal motion. This process, called laser cooling, uses carefully tuned beams of light to gently push against atoms moving in any direction, slowing them the way a series of perfectly timed gusts of wind might slow a ball rolling across a floor, regardless of which way it happened to be rolling. Combined with additional techniques involving magnetic traps, scientists have cooled clouds of atoms down to temperatures measured in mere billionths, and in some experiments, trillionths, of a single Kelvin above absolute zero. At these temperatures, something extraordinary happens to matter itself. Atoms cooled this close to absolute stillness begin to lose their individual identity in a strange quantum sense, spreading out and overlapping until they behave as a single, unified entity rather than a collection of separate particles. This exotic state of matter is called a Bose-Einstein condensate, named after the physicists whose theoretical work predicted its existence decades before anyone had the technology to actually create one. A Bose-Einstein condensate, created in a laboratory on Earth, can reach temperatures colder than any naturally occurring place ever measured in the observable universe. Colder even than the expanding gas of the Boomerang Nebula. Colder than the depths of intergalactic space. Colder than the ancient afterglow of the Big Bang itself. This means that, for a brief moment, inside a chamber smaller than a refrigerator, sitting on a table in a physics building somewhere on Earth, the coldest patch of matter in the known universe exists, created deliberately, studied carefully, and then allowed to warm again once the experiment concludes. It is a strange thought that human ingenuity, working entirely within Earth's own atmosphere, has managed to briefly outdo every natural process the entire universe has produced across billions of years of cosmic history when it comes to approaching that theoretical floor of absolute zero. Nature, left to its own devices across unimaginable stretches of time and space, has produced places a single degree above absolute zero. A handful of physicists, working over a period of mere decades, have produced conditions closer still, if only for a few careful, fleeting seconds at a time. Moving back out into the cosmos itself, away from laboratories and back toward the natural landscape of cold that fills the universe. There are entire categories of objects whose very existence depends on extreme, isolated cold in ways that reveal just how varied this landscape truly is. Consider a rogue planet, a world that formed around a star, or perhaps formed independently within a collapsing cloud of gas, only to be ejected entirely from its system by a gravitational encounter with another massive body. These worlds drift alone through the galaxy, unattached to any star, receiving no meaningful warmth from stellar radiation at all. Their only source of internal heat coming from whatever residual warmth remains from their formation, and from the slow decay of radioactive elements buried deep within their cores. The same process that keeps Earth's interior molten billions of years after our planet first formed. Without a nearby star, a rogue planet's surface would settle into a temperature dictated almost entirely by that faint internal warmth, and by the same cosmic microwave background radiation bathing every corner of the universe, likely landing somewhere in the range of just a few tens of degrees above absolute zero, an almost unimaginably frigid, permanently dark world, drifting silently between the stars. Astronomers estimate that rogue planets may be surprisingly common, potentially numbering in the billions within our galaxy alone, vastly outnumbering the visible, starlit worlds we are more familiar with, each one a solitary, frozen wanderer, carrying whatever atmosphere it managed to hold on to, frozen solid against its surface, with nothing but starlight from impossibly distant suns, offering the faintest specks of illumination across skies that never brighten into anything resembling a true day. If a rogue planet happened to carry enough internal heat, perhaps from a molten core warmed by radioactive decay, it is even conceivable that liquid water could persist deep beneath a frozen crust, sealed away from the crushing cold above by nothing more than the insulating layer of ice itself, not unlike conditions scientists suspect exist on certain moons within our own solar system. This brings the story back toward more familiar territory, to icy worlds that do orbit a star, yet remain so far removed from its warmth, or so effectively shielded by other means, that they too maintain deep, frigid cold at their surfaces, while harboring surprising warmth and even liquid water hidden below. Europa, one of Jupiter's 4 large moons, presents a striking example of exactly this contradiction. Its surface, a cracked and frozen shell of water ice, sits at an average temperature around -171 degrees Celsius. cold enough that the ice itself behaves more like solid rock than anything resembling the ice found in a household freezer. Yet beneath that frozen shell, scientists have gathered increasingly strong evidence for a vast, liquid ocean, kept from freezing solid by the constant flexing and squeezing Europa experiences as it orbits Jupiter. Caught in a gravitational tug-of-war between the giant planet and its neighboring moons. That flexing generates internal friction, and friction generates heat, enough heat, apparently, to maintain a liquid ocean beneath dozens of kilometers of ice, on a moon whose surface temperature never rises anywhere close to the freezing point of water. Saturn's moon Titan tells a related but distinct story, a world cold enough, at around -179 degrees Celsius, that water ice behaves as bedrock, while an entirely different substance, liquid methane and ethane, takes on the role water plays on Earth, filling lakes, carving river channels, and falling as rain from a thick, hazy atmosphere. Titan demonstrates something important about how we ought to think about cold and habitability together. The rigid assumption that cold automatically means lifeless, sterile, and inactive breaks down the moment you consider a world where an entirely different set of chemicals remains liquid at temperatures that would freeze anything familiar from Earth solid within moments. Cold, in other words, is always relative to the specific chemistry involved, and a landscape that looks catastrophically frozen by Earth's standards can still host rivers, rain, and slow, patient geological activity, provided the right materials are present to remain liquid at those temperatures. Returning to our own solar system's outer reaches, the Kuiper Belt, that vast, disc-shaped region of icy bodies extending well beyond Neptune's orbit, hosts a population of frozen worlds including Pluto, whose surface temperature drifts between roughly -223 and -233 degrees Celsius, depending on its position along its long, elliptical orbit around the Sun. At that distance, ranging between roughly 4.5 billion kilometers and 7.5 billion kilometers from the Sun, depending on where it sits along its long, elliptical path, sunlight arrives so diminished that even at local noon, standing on Pluto's surface would feel more like a deep twilight than anything resembling daylight, the Sun itself appearing as little more than an unusually bright star, offering almost none of the warmth so easily taken for granted here on Earth. Comets, many of which originate from the even more distant Oort cloud, a theoretical spherical shell of icy bodies surrounding the entire solar system at distances measured in trillions of kilometers, spend the overwhelming majority of their existence in this deep, distant cold, only occasionally swinging inward toward the Sun on orbits that can take thousands or even millions of years to complete a single loop. During that long, cold stretch of their orbit, comets are essentially inert, frozen solid, indistinguishable in behavior from any other icy rock drifting through the darkness. It is only the sudden proximity to the Sun's warmth, during their brief inward passage, that triggers the dramatic transformation most people associate with comets, ice turning directly into gas without ever becoming liquid, a process called sublimation, streaming outward to form the glowing coma and the long, sweeping tail that make comets such striking sights when they do pass near enough to be seen. This cycle, deep frozen dormancy followed by brief, dramatic activity near the Sun, illustrates once again how cold in space functions less like a fixed, permanent state and more like a default condition, always ready to reassert itself the instant a source of warmth is removed or left behind. There is one more scale worth considering, larger than any planet, moon, or even any single star system, a scale at which the paradox of hot but harmless plasma first encountered in the thin interstellar medium detected by the Voyager spacecraft, repeats itself on a scale spanning millions of light-years. Galaxy clusters, the largest gravitationally bound structures in the universe, containing hundreds or even thousands of individual galaxies bound together by gravity, are filled with an extremely thin, extremely hot plasma occupying the space between the galaxies themselves, called the intra-cluster medium. This plasma, heated by the tremendous gravitational energy released as matter fell into the cluster over billions of years, can reach temperatures in the tens of millions of degrees, hot enough to shine brightly in X-ray light, providing astronomers one of their most useful tools for mapping the location and structure of galaxy clusters across the observable universe. Yet, exactly as with the plasma detected by Voyager in our own solar system's neighborhood, this intra-cluster medium is so extraordinarily thin, so sparse in terms of actual particles packed into any given volume, that despite its blistering technical temperature, it would provide almost no warmth whatsoever to any solid object placed within it, for the same fundamental reason explored earlier, that temperature measures particle speed, not the density or total quantity of thermal energy available to transfer. A spacecraft drifting through the outskirts of a galaxy cluster, bathed in plasma technically hotter than the surface of most stars, would still find itself losing heat overwhelmingly through radiation into the surrounding void, its net temperature settling far closer to that familiar cosmic floor of a few degrees above absolute zero than to anything resembling the tens of millions of degrees registered by the sparse, fast-moving particles surrounding it. This repeating pattern, hot plasma and cold practical experience existing simultaneously at every scale, from a single solar system to the largest structures in the universe, reveals something almost philosophical about how thoroughly our everyday intuitions about heat and cold, built entirely within the dense, forgiving environment of Earth's atmosphere, fail to translate cleanly into the sparse, extreme conditions found almost everywhere else. Between these enormous galaxy clusters lie the truly emptiest regions known to exist, vast cosmic voids stretching hundreds of millions of light-years across, containing only a scattering of isolated galaxies compared to the dense clusters and filaments surrounding them. Some researchers studying the cosmic microwave background have identified an unusually cold region within it, an area popularly nicknamed the cold spot, where the background radiation registers slightly, though measurably, cooler than the surrounding sky. One leading explanation ties this anomaly directly back to the existence of an enormous, largely empty void along that particular line of sight, a region so underdense that light passing through it loses a small amount of additional energy on its long journey to our telescopes. A subtle effect tied to the way light interacts with the gravitational structure of the regions it crosses on its way across billions of light-years of cosmic history. Whether or not this particular explanation turns out to be the full and final answer, and researchers continue investigating alternative explanations as well, the cold spot serves as a reminder that even the faint, ancient afterglow of the Big Bang is not perfectly uniform, but carries within it the subtle imprint of every structure and every emptiness that light has passed through on its long journey across the universe to reach us. Tracing this story back to its true beginning brings us to the earliest moments after the Big Bang itself, a period during which the entire concept of cold, as anything we would recognize, simply did not yet apply. In the first fraction of a second after the universe began, temperatures were so extraordinarily high, potentially exceeding values that current physics struggles even to describe with confidence, that the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces may have existed unified as a single force, only splitting apart into their familiar, separate forms as the universe expanded and cooled within those first fleeting instants. As expansion continued, the universe cooled through a series of distinct thresholds, each one triggering a fundamental transformation in the nature of matter and energy itself. Within the first few minutes, as temperatures dropped enough for protons and neutrons to bind together without immediately being blasted apart again by the surrounding heat, the lightest atomic nuclei formed, hydrogen, helium, and a trace amount of lithium, in a process called Big Bang nucleosynthesis, effectively setting the basic chemical recipe from which every star, planet, and living thing would eventually be assembled. For hundreds of thousands of years afterward, the universe remained too hot for those nuclei to capture electrons and form complete, neutral atoms, remaining instead as an opaque plasma, a fog of charged particles that scattered light constantly, preventing it from traveling freely in any direction. Only once the universe had cooled enough, roughly 380,000 years after the Big Bang, could electrons finally settle into stable orbits around atomic nuclei, forming the first neutral atoms in a period astronomers call recombination. At that exact moment, the universe became transparent for the first time, and light was finally free to travel across space without being immediately scattered. And that very same light, stretched enormously by billions of years of subsequent cosmic expansion, is precisely the cosmic microwave background radiation still detectable in every direction today. The faint, cooling afterglow explored earlier in this very story. Every stage of this history represents cooling, a universe moving steadily, irreversibly, from an initial state almost too hot to describe, toward the frigid, expansive emptiness that characterizes the vast majority of space today and will continue to define its character for as long as the universe continues to exist. This same relentless cooling awaits our own solar system, though on a timescale that dwarfs any human concern, stretching across billions of years still to come. In roughly 5 billion years, the Sun will exhaust the hydrogen fuel currently sustaining the nuclear fusion in its core, swelling dramatically into a red giant, likely engulfing or at least scorching the inner planets, including quite possibly Earth itself, before eventually shedding its outer layers entirely, leaving behind a small, extraordinarily dense remnant called a white dwarf. That white dwarf, no longer generating any new energy through fusion, will begin the same long, slow cooling process explored earlier, radiating away its residual heat across trillions of years, far outlasting the current age of the universe by an enormous margin, eventually approaching, in the almost unimaginably distant future, temperatures close to that same universal floor set by the ever-cooling cosmic microwave background. Everything, in the end, points toward the same direction, the same slow, patient drift toward cold, whether examining a single aging star, a solitary rogue planet drifting between galaxies, the largest cluster of galaxies bound together by gravity, or the universe considered as one single, evolving whole. There is something worth sitting with in this pattern, a detail easy to overlook amid all the specific numbers and specific places. The arrow of time itself, the reason we experience the past as fixed and the future as open, the reason eggs break but never spontaneously reassemble, is deeply tied to this same underlying tendency toward increasing entropy, toward energy spreading out, becoming less concentrated, less able to do further work. Cold, in this sense, is not merely one physical property among many scattered across the universe. It is closely woven into the very fabric of why time seems to move in the direction it does at all. Why the universe had a beginning full of concentrated energy and heat, and appears headed toward an ending characterized by the opposite. Energy spread so thin and so evenly, that no meaningful difference, no engine for change, remains anywhere at all. It is worth stepping back briefly to consider how humans even arrived at the concept of absolute zero in the first place, because the idea did not emerge from studying space at all. It emerged from studying gases, engines, and the behavior of ordinary matter right here on Earth. During the early industrial era, in the early 1800s, scientists studying how gases expand and contract as they are heated and cooled noticed something remarkably consistent. For every degree a gas was cooled, its volume shrank by a predictable, steady fraction. And if you extended that pattern mathematically, following the trend down and down, it pointed toward a single temperature at which a gas would theoretically shrink to zero volume entirely. That temperature, calculated purely from extrapolating a simple, observed pattern, landed remarkably close to what we now call absolute zero, long before anyone had the technology to actually approach it experimentally, and long before anyone had any direct evidence that such a floor genuinely existed anywhere in nature at all. The physicist William Thomson, later known as Lord Kelvin, formalized this idea into an entire temperature scale in the middle of the 1800s, proposing that temperature should be measured from this theoretical absolute floor, rather than from arbitrary reference points like the freezing or boiling point of water. This is why the scale scientists use today carries his name, the Kelvin scale, starting at zero and rising from there, with no negative numbers required, because nothing can exist below that floor in the first place. What makes this piece of history remarkable is that the concept of absolute zero, and the entire Kelvin scale built around it, was developed almost entirely through reasoning about steam engines and laboratory gases, decades before anyone had measured the temperature of interstellar space, decades before anyone had detected the cosmic microwave background, and well over a century before the Boomerang Nebula was identified as the coldest known natural place in the universe. Humans figured out the mathematical floor of cold before they had any tools capable of confirming just how close the universe itself actually comes to that floor in its most extreme, isolated corners. It is a reminder that some of the deepest truths about the cosmos were worked out not by staring upward through a telescope, but by paying close, careful attention to very ordinary things happening in laboratories, kitchens, and engine rooms, right here on the surface of our own planet. Speaking of the surface of our own planet, it is worth pausing on just how cold Earth itself can become, if only to appreciate the scale of difference that still separates even our harshest environments from the depths of space. The coldest temperature ever recorded on the surface of Earth was measured at a research station in Antarctica, where conditions dropped to approximately -94 degrees Celsius. That number represents something close to the practical limit of how cold our planet's own atmosphere can become, shaped by the combination of extreme elevation, extreme dryness, and the long, sunless winter that settles over the continent for months at a time. And yet, staggering as that figure is by any human standard, it remains dramatically warmer than the shadowed lunar craters explored earlier, warmer still than the surface of Pluto, and almost inconceivably warmer than the 1 degree above absolute zero measured in the expanding gas of the Boomerang Nebula. Even Earth's single coldest recorded moment, the most extreme our entire planet's atmosphere has ever produced, sits closer in temperature to a comfortable spring day than it does to the natural cold found scattered throughout the rest of the universe. This comparison helps place human experience honestly within the larger picture. Nothing that has ever happened to a human being standing on the surface of Earth, no blizzard, no polar expedition, no Arctic research station, has ever come remotely close to the kind of cold that exists as an ordinary, unremarkable baseline across most of the observable universe. Our entire species has lived out its whole history bathed in warmth that the rest of the cosmos would consider a strange and fleeting exception. This becomes especially clear when engineers try to build instruments capable of studying the universe in certain kinds of light, because sometimes the challenge is not keeping something warm against the cold of space, but deliberately embracing that cold as an essential tool. The James Webb Space Telescope offers one of the clearest examples of this principle in action. Designed to observe the universe primarily in infrared light, a type of radiation closely tied to heat itself, the telescope faced an unusual problem before it ever captured a single image. Any warmth in the telescope's own instruments would generate infrared radiation of their own, effectively blinding the telescope with its own heat before it ever had a chance to detect the faint infrared glow arriving from distant galaxies. To solve this, engineers designed the telescope with an enormous, multi-layered sunshield, roughly the size of a tennis court, positioned to block sunlight and Earth's own heat from ever reaching the delicate instruments and mirrors on the opposite side. This shield does not simply block sunlight the way a single umbrella might. It consists of 5 separate layers, each one thinner than a human hair, spaced apart in a careful arrangement that allows heat absorbed by each layer to radiate away sideways into space before it can reach the next layer inward. By the time heat would theoretically pass through all 5 layers, its intensity has been reduced dramatically, allowing the telescope's own instruments, positioned on the shielded side, to cool passively down to temperatures around -233 degrees Celsius, just a handful of degrees above absolute zero. Certain especially sensitive instruments aboard the telescope require even colder conditions, still cooled further using a dedicated mechanical refrigeration system, because even the passive cooling provided by the sunshield alone is not sufficient for their extraordinarily delicate detectors. In this case, cold is not a threat engineers are fighting against. It is the entire operating principle that makes the telescope's most important scientific work possible in the first place, allowing it to detect the faint infrared light traveling from some of the earliest, most distant galaxies ever observed. Light that has been stretched and dimmed by billions of years of cosmic expansion into wavelengths, only detectable against a background colder than almost anywhere else humans have ever built, operated a piece of technology. This same tension between fighting cold and embracing it appears in a very different form aboard the Voyager spacecraft, both of which continue transmitting data back to Earth from interstellar space decades after their launch. Powered not by solar panels, which would be useless so far from the sun, but by a technology called a radioisotope thermoelectric generator. These generators work by harnessing the steady, reliable heat given off by the natural radioactive decay of a small amount of plutonium, converting a portion of that heat directly into electricity to power the spacecraft's instruments, transmitters, and internal heaters. That heat serves a second, equally critical purpose beyond generating electricity. It keeps the spacecraft's internal components warm enough to continue functioning, even as the external environment around the spacecraft has grown colder and colder with every passing year of its journey outward, first through the frigid outer solar system, and eventually into the strange, technically hot but practically frigid plasma of true interstellar space explored earlier in this story. Without that continuous, radioactive warmth, the delicate electronics inside Voyager would have stopped functioning decades ago, its instruments and internal wiring becoming too cold to operate reliably, effectively silencing the spacecraft long before it ever reached the boundary of our solar system. Engineers designing that mission, back in the 1970s, had to account for a journey stretching across timescales and through environments that would place the spacecraft farther from any source of stellar warmth than any human-made object had ever traveled before. And the solution they settled on, a small chunk of steadily decaying radioactive material, continues quietly generating just enough warmth to keep a piece of 1970s technology alive and communicating, even now, far beyond the edge of our sun's protective influence. There is one more environment worth considering, a category of world that pushes the contrast between light and shadow to its most extreme possible expression, beyond even the Moon or Mercury explored earlier. Certain exoplanets, worlds orbiting other stars, have been found in what astronomers call tidal locking, a state where a planet's rotation has synchronized so precisely with its orbit that the very same side of the planet always faces its star, exactly the way the same side of our own moon always faces Earth. For a tidally locked planet, this means one hemisphere exists in permanent, unending daylight, baked continuously by direct starlight with no relief, while the opposite hemisphere exists in permanent, unending night, receiving no direct starlight whatsoever, for as long as the planet continues to exist. On certain tidally locked worlds identified by astronomers, particularly those orbiting extremely close to their host star, models suggest the permanently sunlit side could reach temperatures hot enough to melt rock or metal, while the permanently dark side, cut off entirely from any direct stellar warmth, could plunge low enough to freeze even nitrogen and oxygen directly out of any atmosphere present, essentially causing a planet's own air to snow out of the sky and settle as frost across its perpetually dark hemisphere. Depending on the thickness and composition of a given planet's atmosphere, and how efficiently it manages to carry warmth from the scorched daylight side toward the frozen night side through global wind patterns, this contrast can be softened somewhat. But on planets with thin atmospheres, or none at all, the difference between the two permanent hemispheres can be more extreme than anything found anywhere in our own solar system. A single world containing what amounts to a permanent inferno and a permanent deep freeze, separated only by the invisible line running along its equator, called the terminator, where perpetual daylight meets endless night. Stepping back from these distant, alien worlds towards something far closer to home, it is worth asking why cold feels the way it does to a human body in the first place. Since so much of the fascination with extreme cold in space comes from imagining what it would feel like, even though, as explored earlier, sensation itself depends entirely on the presence of matter to conduct that feeling. Human skin contains specialized nerve endings called thermoreceptors, tuned to detect changes in temperature and to send signals to the brain, interpreting those changes as heat or cold. These receptors did not evolve to measure absolute temperature the way a thermometer does. They evolved to detect rates of heat loss or heat gain from the skin's surface, which is precisely why a metal railing feels colder to the touch than a wooden fence post sitting at the exact same ambient temperature, because metal conducts heat away from your hand far more efficiently than wood does, triggering a stronger cold signal even though both surfaces are, technically, identical in temperature. This detail connects directly back to the earlier explanation of why an astronaut exposed to the vacuum of space would not experience anything resembling the instant, biting cold of touching ice or metal in freezing weather here on Earth. Without matter present to conduct heat away rapidly, the specific sensory signal humans associate with cold, that immediate, sharp feeling of heat draining from skin, simply would not fire the same way, even in an environment that is, by any strict physical measurement, extraordinarily cold. Frostbite, the genuine tissue damage humans can suffer in extreme cold, results from ice crystals forming within cells and from blood vessels constricting to preserve warmth in the body's core at the expense of extremities. A biological response finely tuned over the course of human evolution for surviving cold climates on Earth's surface, not for surviving exposure to a vacuum where the physics of heat loss operates by an entirely different, much slower mechanism. This gap between our evolved, Earth-shaped instincts about cold and the very different physical reality of cold in space may be part of why so much popular imagination about space depicts instant freezing, when the actual danger, as explored earlier, comes overwhelmingly from pressure and oxygen loss rather than temperature at all. Perhaps because of this same instinctive fascination with cold as something almost supernatural in its power, human culture has long been drawn to the idea of using extreme cold deliberately, as a way of pausing biological time itself. Cryonics, the practice of preserving a human body, or in most cases currently just the brain, at extremely low temperatures using liquid nitrogen, rests on the hope that future technology might eventually reverse the damage caused by the cooling and freezing process, reviving a person long after the moment their body was legally declared to have stopped functioning. Liquid nitrogen, used in these procedures and in countless laboratory and medical applications, sits at a temperature of about -196 degrees Celsius, remarkably cold by any human standard, and yet, once again, nowhere close to the deep cold found scattered naturally throughout the universe. Even liquid helium, used in even more extreme laboratory cooling applications, and required to reach the frigid operating temperatures of certain superconducting materials, only reaches around -269 degrees Celsius, tantalizingly close to absolute zero, yet still measurably above it, and still, remarkably, warmer than the natural gas expanding outward from the Boomerang Nebula. This persistent gap between our most extreme technological achievements in cooling and the coldest naturally occurring conditions found in the universe reveals just how extraordinary that aging star's expanding gas cloud truly is, a place where nature, through nothing more complicated than rapid gas expansion, briefly outpaced almost every deliberate cooling effort humans have ever engineered, outside of the specialized quantum experiments explored earlier. One final environment deserves mention, precisely because it seems, at first glance, like it should be the most extreme example of cold found anywhere, and yet turns out to be more complicated than that simple assumption suggests. Sagittarius A, the supermassive black hole sitting at the center of our own galaxy, is often imagined as an object defined by absolute darkness and absolute cold, a place where nothing, not even light, can escape. And in a narrow, technical sense, the region immediately surrounding an isolated black hole, far from any surrounding matter, would indeed settle toward that same frigid cosmic floor set by the background radiation filling the rest of the universe. Since a black hole itself, on its own, emits only an extraordinarily faint trickle of radiation through the process called Hawking radiation, mentioned earlier, far too faint to provide any meaningful warmth. But Sagittarius A, like most large black holes actually observed by astronomers, is rarely found in true isolation. It is typically surrounded by an accretion disk, a swirling ring of gas and dust spiraling inward under the black hole's immense gravity, compressed and heated through friction and gravitational stress to temperatures reaching millions of degrees, generating some of the most intense radiation observed anywhere in the universe, easily visible to telescopes designed to detect X-rays and other high-energy light. This creates a strange, almost contradictory environment, an object whose very name has become a popular symbol of cosmic cold and darkness, surrounded instead by some of the hottest, most energetic material found anywhere in the observable universe. a reminder that even our most famous cosmic landmarks resist the simple, single-word descriptions popular imagination likes to assign them. The true darkness and cold associated with a black hole exists specifically within and immediately beyond its event horizon, that boundary beyond which nothing, including light, can escape, a genuinely isolated pocket of near-absolute stillness, sitting at the heart of a structure surrounded, in most real observed cases, by some of the most violently hot material the universe has ever produced. There is one more use of the word cold worth exploring, because it appears in cosmology in a way that has nothing to do with temperature at all. And understanding the distinction clarifies just how differently the same word can be applied depending on context. Cosmologists frequently refer to something called cold dark matter, the leading theoretical framework describing the mysterious, invisible substance that appears to make up roughly a quarter of the total mass and energy content of the universe, vastly outweighing all the visible stars, planets, and gas combined. In this context, the word cold does not describe temperature in the way every other example in this story has used it. It describes velocity, specifically referring to particles that move slowly compared to the speed of light, a property that allowed dark matter to clump together gravitationally in the early universe, forming the scaffolding upon which galaxies and galaxy clusters eventually assembled. If dark matter particles had instead been moving at extremely high speeds close to the speed of light, a scenario cosmologists describe using the competing term hot dark matter, they would have been too fast-moving to clump together effectively, smoothing out into a nearly uniform haze rather than collapsing into the dense structures required to seed galaxy formation. Observations of the actual large-scale structure of the universe, the way galaxies cluster together into filaments and sheets surrounding enormous voids, strongly favor the cold dark matter model over its hot alternative, suggesting that whatever this mysterious substance actually turns out to be, it behaves, at least in this specific technical sense of slow relative motion, as cold. This is a useful reminder that scientific language often borrows familiar, everyday words and repurposes them with precise, sometimes surprising technical meanings, and cold, throughout physics and cosmology, carries several distinct definitions depending on whether the conversation concerns particle motion, thermal radiation, or the practical experience of an object losing energy to its surroundings. Cold also plays a quiet but essential role in an entirely different part of cosmic history, the very process by which planets like Earth first assembled out of the swirling disk of gas and dust surrounding our young, newly formed sun. Within that early disk, temperature varied dramatically, depending on distance from the forming sun at its center, hot and turbulent close in, cooling steadily further out. Exactly the same basic principle explored throughout this story applied to the very earliest stages of our solar system's history. At a certain distance from the young sun, temperatures dropped low enough for water and other common compounds like methane and ammonia to freeze solid rather than remaining as vapor mixed throughout the surrounding gas. Astronomers call this boundary the frost line, sometimes referred to as the snow line, and its location had an enormous, lasting influence on the architecture of our entire solar system. Inside the frost line, where temperatures remained too warm for these compounds to freeze, only rock and metal could condense into solid material, which is why the inner planets, Mercury, Venus, Earth, and Mars, are comparatively small, dense, rocky worlds built from the limited supply of solid material available in that warmer inner region. Beyond the frost line, where ice could form abundantly alongside rock and metal, planets had access to a vastly larger supply of solid building material, allowing them to grow far larger, eventually massive enough to gravitationally capture huge surrounding envelopes of hydrogen and helium gas directly from the disk, forming the enormous gas giants Jupiter and Saturn, along with the somewhat smaller but still substantial ice giants Neptune and Uranus. In other words, the entire size and composition contrast between the small rocky planets of our inner solar system and the enormous gas and ice giants of the outer solar system traces directly back to a boundary defined purely by temperature, by exactly where, within that ancient swirling disk, conditions first grew cold enough for ice to exist as a solid rather than a vapor. Cold, in this sense, did not just shape individual worlds after their formation, the way it shapes lunar craters or aging stars. It shaped the entire blueprint of which kinds of planets could form where in the first place, setting the basic architecture of our solar system billions of years before any of those planets had fully finished assembling. This same cold, which proved so essential in building our solar system, has also proven to be one of the most persistent and dangerous adversaries facing human missions sent to explore other worlds, particularly Mars, a planet whose thin atmosphere provides only a fraction of the insulating protection Earth's atmosphere offers. The Opportunity rover, which explored the Martian surface for nearly 15 years, far longer than its original planned mission of just 90 days, ultimately lost contact with mission controllers on Earth, not because of any single mechanical failure, but because of an enormous dust storm that blanketed the planet, blocking sunlight from reaching the rover's solar panels for an extended period. Without power generated from sunlight, Opportunity's internal heaters stopped functioning, and Martian nighttime temperatures, which regularly plunged to around -70 degrees Celsius, even under normal conditions, were almost certainly enough to permanently damage the rover's internal electronics and batteries during that extended, unpowered cold spell. Mission engineers attempted repeatedly to re-establish contact once the dust storm cleared. But after months of silence, the rover was declared lost. Its mission concluded not by any dramatic single event, but by the quiet, patient cold of a Martian night, arriving over and over, with no power available to hold it back. This same fundamental challenge, keeping delicate electronics warm enough to function through the brutally cold Martian nights, shapes the design of nearly every mission sent to the planet's surface, requiring careful combinations of insulation, small internal heaters, and in some cases, the same kind of radioisotope power sources used aboard the Voyager spacecraft, converting the steady heat of radioactive decay into both electricity and warmth, precisely because relying on sunlight alone leaves a mission vulnerable to exactly the kind of extended, unpowered cold spell that ultimately silenced Opportunity. This persistent difficulty in fighting off cold, whether aboard a rover on Mars or a spacecraft drifting through interstellar space, connects to a deeper, more fundamental principle in physics, one explaining why approaching absolute zero becomes progressively, almost absurdly, more difficult the closer you actually get to it. This principle is sometimes summarized as the third law of thermodynamics, which states, in essence, that reaching absolute zero exactly would require an infinite number of steps, or infinite energy, making it a limit that can be approached ever more closely, but never, under any circumstances, actually reached. Each incremental step colder requires disproportionately more effort, more energy, and more sophisticated technology than the step before it, which is precisely why the extraordinary laboratory techniques explored earlier, involving lasers and magnetic traps, represent decades of dedicated engineering effort just to approach within a tiny fraction of a single degree of that theoretical floor, and why even that remarkable achievement still falls short of absolute zero itself by a measurable, if vanishingly small, amount. This same principle applies, at a cosmic scale, to the far future heat death of the universe explored earlier, a state of maximum entropy that the universe will approach ever more closely across almost incomprehensible stretches of time, without ever technically, precisely arriving at perfect uniformity, always approaching. In the same way our best laboratory experiments approach absolute zero, but mathematically never quite touching that final theoretical limit. There is one final category of object worth exploring, because it sits in a strange, uncomfortable middle ground between a star and a planet, and because one particular example of it holds a temperature record that continues to surprise astronomers. Brown dwarfs are objects that form the same way stars do, collapsing out of a cloud of gas under their own gravity, yet never accumulated quite enough mass to ignite full, sustained hydrogen fusion in their cores, the process that powers ordinary stars like our own sun for billions of years. Sometimes described as failed stars, brown dwarfs occupy a strange category. More massive and hotter than any planet, yet never bright or energetic enough to shine as true stars do, radiating away the leftover heat from their formation slowly, over billions of years, cooling continuously the entire time, since they have no ongoing fusion process to replenish the energy they lose. Because of this continuous, unreplenished cooling, older brown dwarfs are consistently colder than younger ones. And astronomers have used this relationship to identify some genuinely extraordinary examples sitting at the very coldest end of this cooling spectrum. One object, known by its catalog designation, was identified drifting relatively close to our own solar system, and its measured temperature came as a considerable surprise when researchers first analyzed it. Rather than the blazing heat associated with even the coolest true stars, this particular brown dwarf registered a temperature somewhere in the range of -50 to -10 degrees Celsius, comparable to the harshest winter conditions recorded in Earth's own polar regions, and utterly unlike anything resembling stellar heat, despite technically belonging to the same broad category of object that includes our own blazing sun. Even more remarkably, observations of this object's atmosphere suggested the presence of water, clouds, condensing out of its atmosphere in a manner conceptually similar to clouds forming in Earth's own sky, an almost unimaginable image. Weather patterns and condensing water vapor occurring within the atmosphere of something astronomers still classify, technically, as a star-like object rather than a planet. This single discovery collapsed, in a strange and wonderful way, the tidy mental boundary many people carry between stars, which are supposed to be blazing hot, and planets, which are supposed to be comparatively cold, revealing instead a smooth, continuous spectrum of temperature stretching from the blistering surface of the hottest, most massive stars all the way down to objects cool enough to host clouds and weather, blurring the line between stellar remnant and planetary atmosphere almost entirely. Younger brown dwarfs, still relatively early in their long cooling process, can register surface temperatures in the hundreds, even low thousands, of degrees Celsius, hot enough to glow faintly in infrared light, though never bright enough to shine visibly the way true stars do. Given enough time, astronomers expect that even these younger brown dwarfs will continue cooling along the same trajectory, eventually approaching temperatures similar to the coldest examples already identified, and perhaps, over sufficiently long stretches of time, cooling further still, approaching that same universal floor set by the cosmic microwave background that limits how cold any object bathed in that ancient radiation can ultimately become. This entire category of object serves as a fitting bridge between two ideas explored earlier in this story: the steady, inevitable cooling that governs neutron stars and white dwarfs alike, and the strange, continuous spectrum connecting stars and planets that appears again and again throughout the universe. Once you start looking closely enough at how temperature actually varies from one object to the next, rather than assuming rigid categories where, in reality, only a smooth, unbroken gradient exists. It also offers a fitting final example for a broader truth that has run underneath every single object and process explored throughout this entire story. Nothing in the universe is simply hot or simply cold in any permanent, fixed sense. Every star, every planet, every drifting cloud of gas, every aging stellar remnant exists somewhere along a long, continuous, ever-changing journey between the searing heat of its own formation and the patient, waiting cold of the universal background that surrounds it on every side. A journey some objects complete in mere minutes, and others stretch out across timescales longer than the current age of the universe itself. All of this has direct, practical consequences for any future in which humans attempt to travel far beyond the protective warmth of our own solar system, whether aboard a probe sent to study another star, or, in a far more ambitious scenario, aboard a vessel carrying an entire community of people across the vast distances separating our sun from its nearest stellar neighbors. The nearest star system to our own, a small triple system called Alpha Centauri, sits roughly 40 trillion kilometers away, a distance so enormous that even traveling at speeds far beyond anything achieved by current spacecraft, a journey there would still likely take many decades, perhaps centuries, depending on the propulsion technology involved. For a spacecraft undertaking a voyage of that length, cold is not a passing concern to be managed for a few hours during a spacewalk, or even for a few years during a mission to Mars. It becomes a permanent, defining condition of the entire journey, since, for the vast majority of that trip, the vessel would be traveling through the same profound emptiness explored earlier, far from any star's meaningful warmth, relying entirely on internal power sources and careful insulation to maintain livable conditions for however long the crossing takes. Any interruption to that internal power, whether from mechanical failure, damage from micrometeorite impacts, or simple equipment aging over a journey stretching across multiple human generations, would expose the interior of such a vessel to exactly the same slow, radiative heat loss explored earlier in the context of an unprotected astronaut, except stretched across an entire habitat and an entire community of people, rather than a single individual in a single suit. Engineers and researchers who have studied the theoretical design of such long-duration, multi-generational spacecraft, sometimes informally called generation ships, consistently identify thermal management as one of the most persistent, unglamorous, yet absolutely critical challenges the design would need to solve, arguably as important as radiation shielding, artificial gravity, or the closed-loop life support systems required to recycle air, water, and food across a journey spanning decades or centuries. Redundancy becomes essential in this context. Multiple independent heating and insulation systems, so that the failure of any single component does not risk the survival of everyone aboard, along with careful placement of the ship's living quarters as deep as possible within its overall structure, using the ship's own mass, its hull, its cargo, its water and fuel reserves, as an additional buffer layer against the cold pressing in from every direction outside. This mirrors, in a way, the same protective role Earth's atmosphere plays for every person alive today, an insulating layer standing between fragile, warmth-dependent biology and the relentless cold of the space beyond, except that aboard a generation ship, that protective layer would need to be built, maintained, and repaired entirely by human hands and human ingenuity. rather than provided freely by billions of years of planetary formation. It is a sobering thought that any civilization attempting to spread beyond its home star system would need to solve as one of its most basic and unforgiving engineering problems. The same fundamental challenge explored throughout this entire story: how to hold a small, precious pocket of warmth together, indefinitely, while surrounded on every side by a universe whose overwhelming default condition is cold. And it is an equally sobering thought, worth sitting with for a moment, that our own planet, without any effort or design on our part at all, has been quietly solving that exact problem for us every single day, for as long as life has existed here, through nothing more than the simple, enormous gift of a thick, warm, forgiving atmosphere wrapped around a world sitting at just the right distance from a star of just the right size and temperature, an arrangement so comfortable, so consistent, that most of us go through our entire lives never once considering just how narrow and how precious that arrangement actually is, when measured against the true, default temperature of almost everywhere else. There is a final, quieter dimension to all of this worth acknowledging, one that has nothing to do with temperature directly, but everything to do with why the cold of space feels, to most people, unsettling in a way that ordinary cold on Earth simply does not. On Earth, cold almost always arrives alongside sound: wind moving through trees, ice cracking underfoot, the distant hum of a world still full of motion and noise around you, even in the depths of winter. In the vacuum of space, sound cannot travel at all, because sound is nothing more than a pressure wave, a disturbance passing from molecule to molecule through a medium like air or water. And without any molecules present to carry that disturbance, there is no mechanism left for sound to exist in the first place. This means the cold of space arrives whenever it does become a genuine threat to a person or a piece of equipment, in total silence, without the auditory cues humans have relied on for their entire evolutionary history to sense danger approaching: a howling wind, cracking ice, the groan of a structure under stress. This combination, profound cold paired with total silence, may be part of why the vacuum of space so consistently unsettles human imagination far more than its actual physical mechanism. The slow, radiative loss of heat explored throughout this story might otherwise justify on its own. It is not that space is instantly lethal in the dramatic, flash-frozen way popular fiction often depicts. It is that space combines an environment fundamentally hostile to human biology, through pressure loss and oxygen deprivation, far more immediately than through cold, with a silence and a stillness that offers no sensory warning at all: no sound, no wind, no gradual signal building toward danger, the way cold typically announces itself here on Earth. Layered on top of this cold and silence is a second, entirely separate hazard that any real mission into deep space must contend with, alongside temperature management, and that is radiation. The same electromagnetic and particle radiation streaming continuously from the sun, and more rarely but far more intensely from distant supernovae and other high-energy cosmic events. Earth's atmosphere and its protective magnetic field, generated deep within the planet's molten core, together shield the surface from the overwhelming majority of this radiation, another quiet, essential gift our planet provides that most people never think to appreciate. Spacecraft and astronauts traveling beyond that protective shield, whether in orbit, on the way to Mars, or drifting through true interstellar space the way the Voyager probes now are, face significantly higher radiation exposure, requiring their own dedicated shielding, entirely separate from the insulation and heating systems designed to manage temperature. In this sense, The true danger of deep space is rarely a single threat acting alone, but a combination: thin or absent atmosphere, extreme and uneven temperature swings, dangerous radiation exposure, and a profound silence offering no natural warning, all layered together, each one requiring its own dedicated engineering solution, and each one becoming more dangerous, more quickly, the moment any single protective system aboard a spacecraft happens to fail. Understanding cold in isolation, as this story has attempted to do, is valuable precisely because it isolates one thread from that larger, tangled fabric of hazards, allowing the underlying physics, radiation, conduction, convection, and the absence of matter, to be examined clearly on its own terms, before folding it back into the fuller, more complicated picture of just how unforgiving, and how quietly unforgiving, the environment beyond our atmosphere truly is. One planetary mystery within our own solar system deserves special attention because it defies the simple assumption that distance from the sun alone determines how cold a planet's atmosphere becomes. Uranus, the seventh planet from the sun, holds the record for the coldest atmospheric temperature ever directly measured among all the planets in our solar system, with cloud top readings dropping to around -224 degrees Celsius. This alone would not be surprising, given how far Uranus sits from the sun's warmth, roughly 2.9 billion kilometers away, a distance so great that sunlight reaching its cloud tops arrives with only a tiny fraction of the intensity familiar here on Earth, faint enough that even at local midday, the sun would appear as little more than an unusually brilliant point of light in a permanently dim, pale sky. What makes this genuinely puzzling is that Neptune, the eighth and most distant planet, sitting roughly 1.5 billion kilometers farther from the sun than Uranus, and therefore receiving noticeably less sunlight, is not actually colder. By simple logic, based purely on distance and the amount of sunlight each planet receives, Neptune should be the colder of the two worlds. Yet measurements consistently show Uranus reaching lower minimum temperatures at its cloud tops than Neptune ever does. The likely explanation lies not in distance from the sun at all, but in each planet's internal heat, the residual warmth left over from its formation billions of years ago, still slowly radiating outward from deep within its interior. Neptune generates and releases a measurable amount of this internal heat, radiating out significantly more energy than it receives from the distant sun, warming its atmosphere from within in a way that partially offsets its greater distance. Uranus, strangely, does not show this same internal heat signature, appearing to radiate away only about as much energy as it receives from the sun, with little to no detectable excess warmth bubbling up from its interior. Researchers have proposed several possible explanations for this difference, including the possibility that a massive ancient collision, the same kind of event thought responsible for tilting Uranus onto its dramatic, nearly sideways rotational axis, may have disrupted the planet's internal heat flow in ways that continue to affect it billions of years later, or that some kind of internal barrier deep within the planet is trapping its residual heat in a layer that prevents it from reaching the surface efficiently. Whatever the precise mechanism turns out to be, Uranus stands as a clear demonstration that a planet's temperature is never simply a function of how far it happens to sit from its star. Internal processes, geological history, and even ancient, long-forgotten collisions can shift a planet's temperature in ways that defy the simple, tidy expectation that distance alone should predict cold. This same lesson, that cold in space is shaped by a tangle of overlapping factors rather than any single simple rule, has appeared throughout this entire journey. From the shadowed craters of the moon to the counterintuitive plasma of the interstellar medium, and Uranus offers one final, elegant reminder of just how often our simplest assumptions about temperature break down the moment we look closely enough at the actual evidence. Mars offers one more striking demonstration of just how far cold can push ordinary chemistry into behaving in ways that would seem impossible on Earth, this time involving the very air of the planet itself. During the long, dark Martian winter, temperatures at the poles drop so low, often below -125 degrees Celsius, that carbon dioxide, the primary component of the planet's thin atmosphere, does something water vapor on Earth never does under natural conditions. It freezes directly out of the air, skipping the liquid stage entirely, and settles onto the polar surface as a layer of solid carbon dioxide ice. The same substance familiar on Earth as dry ice, used to keep things frozen precisely because of how extremely cold it is compared to ordinary water ice. This seasonal freezing is so extensive that a measurable fraction of the entire planet's thin atmosphere, perhaps around a quarter of it by some estimates, condenses out of the air and onto the polar caps each winter, only to sublimate back into gas and rejoin the atmosphere once spring returns and temperatures climb again. This means Mars, unlike Earth, experiences a genuine, planet-wide atmospheric pressure cycle tied directly to the freezing and thawing of its own air at the poles, a cycle driven entirely by how close local temperatures happen to swing toward the freezing point of carbon dioxide itself, a substance that requires cold, far more extreme than anything needed to freeze water. Orbiting spacecraft studying Mars have observed this polar ice cap literally growing and shrinking with the seasons, an enormous, visible, planet-scale demonstration of the same basic principle explored throughout this story, that cold is never a fixed backdrop, but an active, constantly shifting force capable of transforming the very composition of a planet's atmosphere, depending on the season, the latitude, and the amount of sunlight reaching any particular patch of ground at any given time. Returning briefly to a structure explored earlier in this story, the International Space Station relies on far more than reflective blankets and a slow rotisserie-style roll to manage its constant, extreme cycling between sunlight and shadow. Hidden within its structure is an active thermal control system, a network of pumps and radiators circulating a substance called ammonia through external loops specifically designed to absorb excess heat from the station's electronics and life support systems, then carry that heat out to large radiator panels where it can be released into space through the same radiative process explored earlier, before the cooled ammonia circulates back inward to absorb more heat and repeat the entire cycle. This system operates continuously, day and night, sunlight and shadow, because the station's internal equipment, computers, life support machinery, and the astronauts themselves all generate heat constantly through ordinary operation, heat that has nowhere to go on its own in the vacuum of space, since, as explored earlier, there is no surrounding air to carry it away through simple convection. Without this active cooling system working continuously, the interior of the station would steadily overheat from its own internal activity, even while its exterior panels swing between the scorching and freezing extremes explored earlier. A reminder that managing cold and heat in space is rarely about fighting a single, simple enemy, but about carefully balancing two opposite problems simultaneously, keeping dangerous internal heat from building up, while also preventing external cold from creeping in wherever sunlight is temporarily blocked. Astronauts aboard the station have described the ammonia cooling loops as one of the most critical and occasionally troublesome systems they depend on, with occasional leaks or blockages requiring emergency spacewalks to repair, precisely because a failure in this system threatens the delicate thermal balance keeping the entire station livable. In an environment where, as this whole story has shown, the default condition just beyond the hull is never gentle and never forgiving for very long. Among the thousands of exoplanets, astronomers have now confirmed orbiting distant stars. One discovery, made using a technique called gravitational microlensing, revealed a world so far from its star and so cold that it helped expand scientists' understanding of just how frigid a planet can become while still technically orbiting a star rather than drifting freely between them. Gravitational microlensing works by watching for the brief brightening of a distant background star as a foreground star, along with any planets orbiting it, happens to pass almost directly between that background star and our own telescopes. Its gravity briefly acting like a lens, bending and focusing the background star's light in a way that reveals the presence and rough characteristics of the foreground planetary system. Using exactly this method, astronomers identified a planet orbiting its host star at a distance comparable to where Jupiter and Saturn sit within our own solar system, around a faint, small star far dimmer than our own sun. Because the host star provides so little warmth to begin with, and because the planet orbits so far from even that limited source of heat, estimates place the planet's surface temperature at an extraordinarily low value, colder than -220 degrees Celsius, comparable to the coldest measured surface conditions found anywhere among the icy worlds of our own outer solar system. Despite this planet orbiting an entirely different star, light years away from our own. Discoveries like this help astronomers build a broader picture of just how common, frigid, distant worlds are likely to be scattered throughout our galaxy. Since planets orbiting far from dim, common types of stars, which vastly outnumber bright stars like our own sun, would be expected to experience exactly this kind of persistent, extreme cold as their ordinary, permanent condition, rather than as any kind of rare exception. It suggests that worlds resembling the icy, distant bodies of our own solar system, rather than the warmer, sunlit planets closer to home, may in fact represent the far more typical outcome of planet formation across the galaxy as a whole, with warm, temperate worlds like Earth representing a comparatively rare and fortunate exception, rather than any kind of cosmic default. One of the largest deliberately engineered cold environments on Earth exists not in a small tabletop laboratory chamber, but stretched around a ring nearly 27 kilometers in circumference, buried beneath the border of France and Switzerland. The Large Hadron Collider, the enormous particle accelerator operated by CERN, relies on thousands of powerful superconducting magnets to bend and focus beams of particles traveling at speeds approaching the speed of light. These magnets only become superconducting, meaning capable of carrying electrical current with effectively zero resistance, once cooled to extraordinarily low temperatures, requiring a continuous supply of liquid helium to maintain the entire ring at approximately -271 degrees Celsius, only a couple of degrees above absolute zero itself. Maintaining that temperature consistently across a ring, stretching many kilometers long, makes the Large Hadron Collider, according to CERN's own description, one of the coldest extended environments anywhere in the universe that we know of, colder, across that enormous continuous length, than the depths of interstellar space itself, which, as explored earlier, still receives a faint but steady warming influence from the cosmic microwave background filling every direction of the sky. This creates a genuinely remarkable situation that for a ring 27 kilometers around, sitting beneath the surface of Earth, humans have engineered conditions colder than the natural background temperature of most of the universe surrounding our own planet. A deliberate, sustained achievement requiring enormous amounts of energy, infrastructure, and careful engineering simply to hold a narrow tunnel at a temperature that, evidently, requires far more effort to create artificially here on Earth than it does to occur naturally in the emptiness between the stars. It is a fitting final illustration of just how strange and counterintuitive the whole subject of cold truly becomes upon close inspection. That the coldest extended environment scientists have ever built sits not aboard a spacecraft drifting through the vacuum, but underground, on the surface of the one planet in this entire story that spends its every day wrapped in comparative warmth, while achieving, through tremendous deliberate effort, a narrow ring of cold that rivals, and in this specific case even exceeds, the ordinary background chill of the universe stretching endlessly beyond our sky. Engineers planning future permanent habitats on the Moon or Mars have increasingly looked toward a surprisingly simple solution for managing the extreme swings explored throughout this story, one that borrows directly from how Earth's own crust behaves. Just a shallow layer beneath the surface of almost any airless or thin atmosphered world tends to maintain a remarkably stable temperature, insulated from the wild swings between blazing daylight and bitter night experienced at the surface itself, simply because rock and soil conduct heat slowly, smoothing out those extremes the deeper you go. This is why current designs for long-term lunar and Martian bases frequently favor burying habitats beneath a meter or more of loose surface material, called regolith, or constructing them within existing lava tubes, natural underground tunnels left behind by ancient volcanic activity, rather than building exposed structures directly on the surface. A habitat protected this way would face a far gentler, far more manageable thermal environment than the surface above it, shielded from the same extreme day and night swings that make surface structures, and the equipment inside them, so vulnerable to the kind of failure that ultimately silenced the Opportunity rover. In effect, future settlers on other worlds may end up recreating, through careful engineering choices, a small version of the same protective principle. Earth's own atmosphere and crust provide us for free, burying their fragile warmth just deep enough underground to escape the harshest version of the cold waiting at the surface above. It is worth returning, briefly, to how the cosmic microwave background explored earlier in this story was actually discovered, because the story behind that discovery is almost as strange as the radiation itself. In the 1960s, two radio astronomers working at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were using a large, sensitive antenna to study radio signals for entirely unrelated purposes when they began noticing a persistent, faint hiss of microwave noise that seemed to come from every direction in the sky equally, no matter which way they pointed their instrument. At first, they assumed the signal was some kind of equipment malfunction and spent considerable time checking their antenna for faults, even discovering and removing a pair of pigeons nesting inside it, along with what they described as a layer of what they jokingly called white dielectric material left behind by the birds, suspecting this debris might somehow be responsible for the mysterious signal. After ruling out every possible source of equipment error they could think of, the two researchers were eventually connected with a nearby team of physicists who had been independently theorizing that exactly this kind of faint, uniform microwave signal should exist as leftover radiation from the Big Bang itself, if the theory were correct. The persistent hiss Penzias and Wilson had been trying so hard to eliminate turned out to be precisely that predicted signal, the actual afterglow of the universe's own birth, discovered almost by accident while trying to solve what the researchers initially assumed was nothing more than an annoying technical problem with their equipment. This discovery, made not by pointing a telescope purposefully at the sky in search of something specific, but by two scientists trying to eliminate what they believed was unwanted background noise, went on to become one of the most important pieces of evidence ever found supporting the Big Bang theory, and earned Penzias and Wilson a share of the Nobel Prize in Physics roughly a decade later. It is a fitting detail to close on, that the faint, cooling whisper of the universe's own beginning, the same radiation that sets the coldest natural floor for temperature found almost everywhere in the observable cosmos, was first detected here on Earth not through grand, deliberate search, but through the patient, careful process of trying to rule out every mundane explanation first, only to discover that the strange signal refusing to go away was, all along, the oldest light in the entire universe, quietly confirming just how far and how completely everything eventually cools. Taken together, every discovery explored throughout this story, from a pair of nesting pigeons accidentally leading to evidence of the universe's birth, to an aging star's expanding gas, briefly claiming the title of coldest known place in existence, to a 27-kilometer ring of superconducting magnets buried beneath the Swiss countryside, points toward the same underlying truth. Cold is not an incidental detail of the cosmos, a minor footnote sitting quietly in the background, while stars and galaxies do the more dramatic work of shaping the universe. It is one of the oldest, most persistent threads running through the entire story of everything, present at the very first instant the universe began cooling from its unimaginable initial heat, still present in the faint background radiation filling every corner of the sky tonight, and still waiting, patiently, at the far end of whatever future the universe has left to unfold. Standing back from all these individual pieces, the shadowed lunar craters, the sunlit and shadowed sides of orbiting spacecraft, the paradoxical hot but harmless plasma of interstellar space, the ancient afterglow of the Big Bang, the impossibly cold expanding gas of an aging star, the slow cooling of neutron stars and white dwarfs across billions of years, and the almost incomprehensibly distant heat death awaiting the universe as a whole, a single unifying picture begins to emerge. Cold in space is not a single, uniform quality spread evenly across the void, the way casual imagination often pictures it. It is instead an intricate, constantly shifting balance, shaped by exposure to radiation, by distance from stars, by the density or emptiness of the surrounding medium, by the speed at which gas happens to be expanding, and by the relentless, ongoing expansion of the universe itself, stretching every wavelength of light a little longer and every remaining pocket of warmth a little thinner with each passing moment. Understanding this transforms the way the darkness above suddenly feels. It is not an empty, hostile blanket, indifferent and uniform, waiting to swallow anything unfortunate enough to drift into it. It is instead an active, evolving, endlessly varied landscape of temperature, shaped by every star that has ever burned, every galaxy that has ever formed, every photon of ancient light still traveling outward from the universe's own fiery birth, each one carrying just a little less energy than it once did, cooling the cosmos, ever so slowly, toward a stillness that lies almost unimaginably far ahead in time. Before we go, be sure to like this video and subscribe for more journeys into the cosmos. The next time you look up at a clear night sky, remember that the darkness between those distant points of light is not simply empty and inert. It is the leftover breath of the universe's own beginning, still cooling, still stretching, still settling, ever so slowly, toward a stillness that none of us will ever witness, but all of us, in some small way, are already a part of. Every warm thing you have ever touched, every breath of warm air, every sunrise that gently lifted the night's chill from your skin, borrowed its warmth from a universe that is, on the whole, overwhelmingly, permanently cold, and that has been growing colder, quietly and patiently, since the very first instant it began to exist. We live, all of us, inside a brief, thin, remarkably fortunate exception to the ordinary rule of the cosmos. A small, warm pocket carved out by a star, an atmosphere, and billions of years of fragile, unlikely conditions holding steady, for now, against the deep, waiting cold that fills essentially everything else. Let that thought settle, quietly, the way the universe itself continues to settle, 1 degree at a time, into the long, patient cold that waits at the end of everything. A stillness so distant, so gradual, and so far beyond any human timescale that for now, tonight, under whatever sky happens to stretch above you, the only honest response left is simply to notice the warmth still lingering here for as long as it lasts and to be quietly grateful for it.